So we're going to do a quick review of graphing polar curves. The one we'll start with is r is equal to 3 sine of 3 theta. Because I don't really know what it looks like or need a little bit of review, I'm just going to plug in points. So I'm going to choose theta, and after choosing theta, that's going to give us our r. So we'll choose the basic thetas. Here are the thetas I'm going to plug in. So I'm going to go ahead and see what happens. So if I plug in 0 to 3 theta, it becomes sine of 0, which is 0. So the first point I start out is just at the origin, or in this case we call it the pole. If I plug in pi over 6, I get sine of 3 times pi over 6, which becomes pi over 2. Sine of pi over 2 is 1, so I end up at 3. So pi over 6 is pointing in this direction. What I'm going to do is I'm going to walk out 3 steps. So I'll go 1, 2, 3. So I end up there. At pi over 4, I'm going to get 3 sine of 3 pi over 4, which we all know. Sine of 3 pi over 4 is rad 2 over 2. So I get 3 rad 2 over 2. So 45 degrees, pi over 4 is in that direction, and I'm going to walk out approximately 3 rad 2 over 2 steps, which I'm just going to estimate to be here. Pi over 3, if I plug that in, I get 3 sine of pi. Sine of pi is 0, so I end up back at the origin. Let's pause a moment and talk about how we got to these points. So we started out at the origin, and then we curved over to 3. Because it's polar, I'm going to draw it kind of in a curve fashion, so I'm going to go at it like this. After that, we ended up at pi over 4, which is this point, and then we ended up back at the origin. So I'm going to curve back around to the origin. Let's see where we go next. At pi over 2, it turns out if I plug that in, I'm going to end up with 3 sine of 3 pi over 2. Sine of 3 pi over 2 is negative 1, so I actually end up at negative 3. Pi over 2 is typically in this direction, but since it's negative, I'm actually going to go in the opposite direction. So let's see what that looks like. I'm going to walk out 1, 2, 3. So now my graph will continue on, and it's going to end up over here. Let's plot a few more points and see what happens. Okay, here are the rest of the values. So at 2 pi over 3, I'm back at the origin, which is 0, meaning my curve is just going to come back this way. At 3 pi over 4, I'm at 3 rad 2 over 2. 3 pi over 4 is in this direction. 3 rad 2 over 2 again, I'm just going to estimate. Looks like it's over here. 5 pi over 6, I end up back at 3. So 1, 2, 3 is over there. And then at pi, I end up back at 0, which is over there. So you get a 3-petaled rose curve. A couple things to note. I want you to notice that the path that the curve took is always going in the counterclockwise direction. Secondly, the path that the curve took is always smooth, and you shouldn't have any jagged edges. In general, the graph for the rose curve is given by r is equal to any number, I'll call it b, sine of n theta, or you'll also have b cosine of n theta. N, it turns out, determines the number of petals, and b determines the petal lengths, but you will explore that on your own in the application on the homework. The next graph we're going to graph is called the limison. Let's take a look. So here are the points of our limison. What does it look like? Remember, we want to keep it counterclockwise. We want to keep it as smooth as possible. So it's going to actually loop around, come back out, and form this shape, roughly. A little word on the terminology that I'm expecting you to know. So this part I'm going to refer to as the tip. This part I'm going to refer to as the loop. And this part is going to be, in this case, a y-intercept on that side, and also another y-intercept on this side. Okay, depending on the shape of the limison, you can have x-intercepts. For example, you might have a limison going in this direction that might look something like this, in which case this becomes the tip, this part becomes the loop, and this is an x-intercept, and this over here is an x-intercept. You could have cases also where the limison's loop actually pops out the other end, so although it won't quite have a loop, for the purposes of this exercise, we're going to refer to this still as the tip. This is still a loop, although it ended up on the other side, and these are still the intercepts. So you're going to be using this Mathematica notebook with this application on it. It's going to be helpful to see the numbers so you can figure out what's happening. So it might be good to open up these controls and see what values you're picking. So right now, all I'm graphing is cosine of t, and if I just move theta around, it's going to graph a graph counterclockwise, smooth. And in this case, cosine of t in polar is not very interesting. It's actually just a circle. I can change things around by changing the a, which is going to add a different constant to it. So for example, if I let my a be 1, let's see what the graph looks like. If I trace that out, it actually form what's known as a cardioid, or a butt. If I change my b, move it a certain direction, notice I get my limison there. And if I change it the other way, I get the loop popping out the other way. And here I get a limison facing this way. So what's going to happen is I let my a be 0, and I change my b to some finite number, say 4. As I change my n, I'm going to actually graph different shapes. One of them is going to be a rose. So here's a 4-petaled rose. And notice the path it takes to complete the whole rose curve. If I change it back to n equals 3, for example, let's see what it looks like. So as I move theta, I can trace out the rose curve. And this one only has 3 petals. I want you to note that it actually finished tracing out theta, or the rose curve. You didn't need to go the full 360 before you got the rose curve. Now you can also change it to sine. You can get different graphs, cosine. You can change the value of n as you go and kind of see what happens as you increase the number of petals. So it's your job to answer the questions on this worksheet. Please be prepared to have a quiz on this that you will not be allowed to drop.